In this video, we solve problem 12.4.016 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the principal unit normal vector to the curve at the specified value of the parameter. We have r of t equals t hat, or t times I hat plus 6 over t times j hat. I prefer to write it in component form like this, or for differentiation, it will be helpful if we write our y component like this. And again, we're interested in this principal unit normal vector at t equals 2. Now, in one video, we use method number 2, which involves the tangential and normal components of acceleration. I highly recommend you use this method. It was in the other video. It's computationally simpler because we're able to substitute t equals 2, lowercase t equals 2, much sooner. And then we're just using the projection of a onto t hat to find a sub t and the Pythagorean theorem to find a sub n. And once we have a sub t and a sub n, and we've got a and t hat, which are relatively easy to compute, we can solve this equation for n hat. Now, in this video, we're going to use the more traditional method. Now, n hat is defined to be the derivative of the unit tangent vector divided by its magnitude. Now, typically, this requires a lot more computation as far as differentiation is concerned. And I'll explain why. In order to just apply this formula, first we need to find t hat. So to find t hat, we need the unit tangent vector that comes from taking the tangent vector, which is r prime, and dividing by its length or magnitude to make it 1 unit long. Now, because we have to take the derivative later, we have to leave this as a function of t. And because we're leaving this as a function of t, and the magnitude of r prime involves the square root of a sum of squared functions of t, this tends to be pretty complicated when we have to take the derivative term by term, or excuse me, component by component for this vector valued function. It will involve typically the quotient rule or the chain rule or both for each of the components. Now, at that point, we're going to end up with a pretty complicated looking function. We could find the magnitude of that complicated looking function and then try to simplify algebraically and then get n of t and then evaluate at t equals 2. But I highly recommend substituting t equals 2 as soon as possible. Now, we can't substitute until we take the derivative, but after we take the derivative, we can evaluate this expression at t equals 2, then find its magnitude at t equals 2. That'll be just finding the magnitude of a vector with numerical components, and then divide to get n hat at 2. Now, if I needed the principal unit normal vector at multiple values of lowercase t, I would probably want to use this formula directly, or maybe use this method in terms of lowercase t. But since I only want n hat at t equals 2, I can plug in t equals 2 right here, and that'll be enough to get us everything that we need to find n hat at 2. So that's the plan. I highly recommend using this method, but if you prefer this method, this is what we'll be covering in this video. So let's start by computing r prime of t and then using that to find the unit tangent. So here's r of t. To find a tangent vector, we compute r prime of t. Just take the derivative component by component. The derivative of t is just 1. The derivative of 6 times t to the negative 1 requires the power rule. So bring that power down, multiply by t to the 1 less power. And that's r prime of t. Or you can write it this way. It's 1 times I hat plus negative 6 over t squared times j hat. Now we want t hat. So that comes from taking this tangent vector and dividing by its length. So once we have that tangent vector, we want to find its magnitude or length by taking the components, squaring them, adding them, and taking the square root. Of course, 1 squared is just 1. And if you've got a fraction, you're squaring it, you'd square the numerator and denominator separately. Negative 6 times negative 6 is positive 36. T squared squared is t to the 4th. Now, I want to get a common denominator over here. So I'll write that 1 as itself over 1. And since I want a common denominator, I need to multiply this 1 by a t to the 4th. That's legal as long as I also multiply the numerator by a t to the fourth. Now the denominators are the same. So we keep the common denominator and add the numerators. And you've got the square root of a fraction. So you can take the square root of the numerator and the square root of the denominator separately. Now the square root of t to the fourth is just t to the 4 divided by 2. We use those properties of radicals and rational exponents. This is t to the 4 over 2, which is t squared. And then this up here, you leave alone. You might be tempted to take the square root of t to the fourth and add the square root of 36, but it doesn't actually work that way. The square root does not distribute over addition or subtraction, so don't try that. All right, so now that we've got r prime, which is a tangent vector or a velocity vector, we've got the magnitude of r prime. If r represents position, the magnitude of the velocity is the speed. Take velocity, divide by the speed, and you're going to get the tangent vector or the unit tangent vector, which points in the direction of motion, but it's exactly 1 unit long. So we're just doing this now. Now dividing by a fraction is the same as multiplying by the reciprocal. Now, if you have a scalar function here, you'll multiply each of the components by that scalar function. And we're about to compute n hat, so we'll have to take the derivative of this. So I recommend writing that square root in the denominator as this function to the 1/2 power. There's a 1 there and an implied 2 there. Now, if I take this and I multiply it by this, the t squareds will reduce and we'll end up with a -6 over t squared plus 36 to the 1/2 power. Oops, that's t to the fourth plus 36 to the 1/2 power. Now we're just going to use this formula. So we need to differentiate. Preparing to differentiate, over here, I see a quotient. I've got a function of t divided by a function of t. So I would use the quotient rule. But here I've got a constant divided by a function of t. This will be easier if I bring this function of t up to the numerator. The differentiation will be easier, I mean. So I'll have -6 times t to the fourth plus 36 to the -1/2 power. Okay, before we go on, let's write down what we did. We computed r prime, then we computed the magnitude of r prime, and then we simplified, and then we computed t hat, which involved taking r prime, velocity vector, and dividing by the speed to get the unit tangent vector. Okay, now n hat is the derivative of the unit tangent divided by the derivative of, or the magnitude of the derivative of the unit tangent. So we're going to take the derivative of this now. Getting ready to use that formula. The derivative of a vector valued function can be found by differentiating component by component. Okay. Now for this x component, since I've got a quotient, I will use the quotient rule. Now remember from calculus 1, the derivative of a quotient is low d high. So it's the bottom function times the derivative of the top function minus high d low over low low. Here's our mnemonic, low d high minus high d low over low low, or low squared if you prefer. And the d is an operator, it applies to whatever's in front of it. So it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function over the bottom function squared. So that's what we're doing here. So it'll be low d high. The derivative of the top function is the derivative of t squared, which is 2t, minus high d low. The derivative of a function raised to the 1/2 power requires the chain rule. Derivative of a function to the 1/2 is 1/2 of that function to the negative 1/2. And you want to put your inside function back inside without differentiating. And then you multiply by the derivative of the inside by the chain rule, which is 4t cubed. This is low d high minus high d low, all over low low. In Filipino or in Tagalog, that means grandpa, lolo. It's not over grandpa, that doesn't make any sense. But if you've got something to a 1/2 power squared, you multiply the exponents, and of course, 2 times 1/2 is 1. So you just end up with a t to the 4th plus 36 in that denominator. Now over here, we're just going to use the chain rule. We've got -6 times a function raised to the negative 1/2 power. So we'll take the derivative of the outside first. So you have -6 times negative 1/2, which is positive 3. So we do that function, 3 times that function to the 1 less power. -1 minus 1 is -3/2. Put the inside function back inside without differentiating, and then multiply by the derivative of the inside. The derivative of t to the 4th is 4t cubed. All right. And we keep going. 1/2 times 4 is 2. So we've got t to the 4th plus 36 to the 1/2 here, times 2t. 2t cubed times negative t squared is going to be a negative t to the 5th. And then we've got t to the 4th plus 36 to the negative 1/2 power, all divided by t to the 4th plus 36. And over here, we've got 3 times 4t cubed, which is 12t cubed, all divided by t to the 4th plus 36 to the 3/2 power. Now here I'd like to simplify a little bit further. It looks pretty bad right now, and if we do a little bit of algebra, it will look a little less bad. I'd like to get rid of that t to the 4th plus 36 to the negative 1/2 power. To do that, I will just multiply by t to the 4th plus 36 to the positive 1/2 power. That's legal as long as we do the same thing in the denominator. And if you're saying to yourself, how did I know to multiply by that? It was because of this rule from algebra. If you take x to some power and x to a different power, you can just add the exponents. I want to add, or I want to multiply by something so that when I add the exponents, I get 0, so that whole thing is gone. So if this exponent is negative 1/2, I need to multiply by exactly the same thing to the positive 1/2, so that this times this will give me something to the 0, which is 1. And that whole term will be gone and everything will simplify really nicely. So that's the plan. Now, when we distribute, we want to think of all of this as one expression, one unit, because we're taking all of that and we're subtracting all of this. So when we distribute this red function in the numerator here, we want to distribute it to this expression underlined in the first, with that first purple underline, and this expression. This to the 1/2 times that to the 1/2 is going to be that to the 1/2 plus 1/2, or to the first, because 1/2 plus 1/2 is 1, times the 2t. And then when we do this times this piece times that piece will give us this expression to the 0, which is 1. So I have 1 times a negative t, or negative 2t to the 5th, all over this down here. I've got this expression to the first times that expression to the 1/2. The bases are the same, you add the exponents. So we'll have t to the 4th plus 36, 1 plus 1/2 is 3/2. All right. So now we distribute. We'll have 2t to the fifth minus, or plus, excuse me, 72t minus 2t to the fifth. Those will reduce, all divided by t to the fourth plus 36 raised to the 3/2. That is the x component of t hat prime. And the y component is, is 12t cubed over this expression. And so we get this. All right. Now, if I needed n hat of t, if I wanted the principal unit normal vector at multiple points on my curve, or at multiple times, if I'm thinking of t as representing time and r as representing position, then I would want n hat of t, and then I would plug in the different values of that lowercase t, that parameter t. But that's not what I want. I want the principal unit normal vector at t equals 2. That means once I've differentiated, I can evaluate this at 2. Then once I have that at 2, I can find its magnitude at 2, which is relatively simple. It's just going to be the magnitude of a vector that has numerical components. And we'll just take that vector, divide by its length, and then we'll find n hat at 2. So that's the plan. We just need to evaluate this at 2 now. And I'm just writing down what we did. We computed t hat prime. And now we're evaluating it at t equals 2. So we'll have 72 times 2 over 2 to the fourth plus 36 to the 3/2. That's our x component. And then our y component is 12 times t cubed over 2 to the fourth plus 36 to the 3/2. Of course, we're replacing all the t's with 2's, and so we get this. So here we'll have a 144 over 16 plus 36 is 52 to the 3/2 power. Over here, we've got 12 times 8. So it's going to be 96 over 52 to the 3/2 power. And we want to find the magnitude of that vector. If you want, you can simplify. So anything to the 3/2 power is itself times the square root of itself. So this is 52 times the square root of 52, because 3/2 is 1 plus 1/2. So it's itself to the first plus itself to the 1/2, which is the square root of itself. And then over here, we're going to have the same type of thing. And of course, 52 has a perfect square as a factor. 52 is the square root of 4 times 13. So I'll have 52 times the square root of 4, which is 2, times the square root of 13, and those denominators. Let's do a little arithmetic and figure out what our components are. So I've got 144 divided by 104. So I get 18 over 13 times the square root of 13. And then for our y component, I've got 96 divided by 104. So that's 12 over 13 times the square root of 13. Okay. Now, n hat is this vector divided by its magnitude at any value of t. So n hat at 2 will be this vector at 2 divided by its magnitude, or t hat prime at 2 divided by its magnitude. And so we'll find the magnitude of this vector now. Take the components, square them and add them and take the square root. So we'll have 18 squared plus 12 squared in that numerator. That's 468 divided by 13 squared times 13. So I'm just going to do the arithmetic on my calculator. 468 divided by 169 times 13 gives me 36 over 169. That works out nicely. Square root of 36 is 6, square root of 169 is 13. So we get 6 over 13. So n hat at 2 is t hat prime at 2 divided by its magnitude. So I've got this vector. And I'm dividing by 6 over 13. So we'll multiply by the reciprocal. And when you multiply a vector by a scalar, you multiply component by component. So when I multiply these two components, or this scalar by this component, the 13s will cancel and 6 will go into 18 3 times. So we'll get 3 over root 13. Over here, the 13s will cancel and 6 will go into 12 twice. So we'll have 2 over root 13. And that is our n hat at 2. And notice that that is the same thing that we got in the other video. So when we used the other method, we obtained the same answer. That's a good sign. So you can use whichever method you prefer. In this video, we just used the standard definition and a lot of differentiation and algebra. In this video, we used more geometry and just a lot of computation, but we had to sort of remember how those pieces were related to each other. I again recommend this, but you can always do this if that's what you prefer. Let me know if you have any questions.